program. I invite all the dignitaries to on stage. Captain Dr. Jason Jacob, Dr. E.D. Dias, Professor K.V. Sinha, Reverend Father Thomas Chakramakil, Professor Krishna Madle, Reverend Father Arun Joske, Professor Chako Jospi, and Dr. Narayanan P.A., convener of the program. Good morning, respected dignitaries, esteemed guests, faculty members, and dear participants. Welcome to the inaugural function of the International Conference on Operators and Spectral Theory, ICOST 2025. Let us commence this auspicious occasion by invoking the blessings of the Almighty. May I request everyone to kindly rise for the prayer.
Thank you for the solemn start. To formally welcome you all, I invite Captain Dr. Jason Jacob, our respected co-convener and head of the department, to deliver the welcome address.
Good morning, one and all. Actually, the Department of Mathematics, St.Aloysius College, is very proud and happy to have you all here at this Lali's residency for the International Conference on Operator Theory and Spectral Theory. This is our third among the series of international conferences that we have been organizing since 2023. Since we are running short of time, I'll be very brief in terms of welcoming our dear guests. First of all, I'd like to welcome one among the leading mathematician of our country and the former director of ISA Kolkata, Professor K.V. Sinha, who is our IAPC chair member to this inaugural session of ICOST 2025. Welcome you, sir. Next, I would like to welcome the two pillars on which we relied completely, Professor Krishna and Professor Emanen. Even though Professor Emanen is not here physically, both of them were very cooperative, and it was based on their inspiration and their words that we started the program, and now we have reached to this inaugural session. So in the name of everyone present over here, let me welcome Professor Krishna and Professor Emanen to this ICOST 2025. Next, I would like to welcome the entire management team of St.Aloysius College, and it includes our manager, Reverend Father Thomas Chakramarkle, CMI, Reverend Father Arun Jo, CMI, the administrator, and Professor E.D. Dias, the principal, and once again our former principal, Professor Chako Jospi. All of them have come over here. They were with us from the very beginning of the conference, at the very beginning of the seed of the conference. All these people were with us. They were inquiring about the progress and everything. So in the name of everyone over here and the name of the entire mathematics fraternity, let me welcome the entire management team to the inaugural session of ICOST 2025. Welcome, sir. And next, I would like to welcome all the distinguished speakers, research scholars, students, everyone present over here from different parts of the world, from different parts of the country, different parts of Kerala, from the neighboring colleges to this inaugural session of ICOST 2025. And last but not the least, let me welcome all my dear students who have been working since months to make this into a reality. Let me welcome once again everyone to this inaugural session. Thank you all.
Thank you, sir, for your warm words. Next, I invite our principal, Dr. E.D. Dias, to deliver the presidential address.
Respected Professor K.V. Singha, member of International Academic Program Committee, our manager Reverend Father Thomas Chakramarkle, CMI, Professor Krishna Mandale, IEPC Chairman, and other dignitaries on and off the dais. All institutions' commitment to promote excellence in education and research. We believe that this conference will not only facilitate the exchange of ideas, but also encourage networking and collaboration among the participants from diverse backgrounds. This conference serves as a platform for bringing together some of the brightest minds in the field of operators and special theory. The Master's Colloquium, an exclusive one-day program for the postgraduate students conducted as a part of this conference, shows the commitment of the organizing committee in promoting the research attitude among the students. I would like to inform you that the Department of Mathematics of our college conducts a program called PRISM every year for the PG students with the same intention. This colloquium provides a golden opportunity for the master's students to interact with eminent mathematicians in the field of operators and special theory. St.Aloysius College proudly acknowledges the financial support from Anusandhan National Research Foundation and the Kerala State Council for Science, Technology and Environment for their financial assistance. I encourage all the attendees to actively participate in the various sessions, engage in fruitful discussions, and take advantage of the networking opportunities available throughout the conference. I wish all the best for the successful conduct of this conference. We may not be able to serve you up to your expectations with our limited resources. Hence, we will try our best to serve you in the maximum possible way with our capacity. We request your wholehearted cooperation. I again wish you all the best throughout this session. Thank you.
Thank you, sir. Now I invite Professor K.B. Sinha, distinguished IAPC member, to deliver the inaugural address.
Good morning. Well, the organizers seem to have made a habit of hitting below the belt. I was not told of this, and I have been assigned 7 minutes, but I promised to finish in 3. I do not have much to say anyway, except to thank the organizers for making this possible, and I am indeed extremely happy to be here, though extremely tired because we arrived rather late last night from Kochi, and nevertheless I am very glad to be here. I see many friendly faces and people whom I have known over the years, and it is always a pleasure to meet up again with them. So I thank again the organizers for having made this possible. Thank you all.
Thank you, Professor. We now proceed to the felicitation segment. Let me first invite Reverend Father Thomas Chakramakil CMI, Manager of St.Aloysius College, Elthuruth, for his felicitations.
Professor Sinha, other dignitaries on the dais, professors, faculty members, research scholars, and dear students. This is the third international conference we are organizing after the MSc course started in our college. And recently the department became a research center, and all the faculty members are trying to be research guides. And they are all engaged in research activities. And that's why they are always interested in organizing such international or national conferences. And I congratulate the department, the faculty members, and also the students cooperating with them in organizing this seminar. And I wish that all the participants will benefit out of this seminar or conference, and it will be a grand success. Thank you.
Thank you, Father.
Next, I call upon Professor Krishna, IAPC Chairperson, to offer felicitations.
Thank you for calling me to speak. It's probably a mistake to ask me to come to the mic. I may not give it up so quickly. It's nice to have a conference here because it's usually not common to have people of the standing of several dignitaries here, several mathematicians here like Professor Sinha, Professor Nakano, Professor Kirsch, and all these people coming to a college in the interior of India. You will see that many of them, including Jaydev and others, the work that they do in mathematics, if you hear them and if you follow them, you will see that the inspiration that you get is something else. So I strongly advise all the PhD students here to attend all the talks, follow them, and you may get inspired by some of the areas that we work in. Finally, let me thank all the organizers, the college, its management, and Narayanan and his colleagues for inviting us here to participate in this conference, and for the excellent facilities you have provided. Thank you.
Thank you, sir.
Now may I request Reverend Father Arun Jose K. CMI, Administrator of St. Aloysius College, Elthuruth, for his words.
Again, good morning to one and all, dignitaries on the dais, and the invited people who have already gathered over here in this auspicious occasion for this inaugural session and the coming 2 to 3 days for the international conference. Once again, I welcome you all to this. Let me tell you, it's a fraternity, mathematical fraternity. More than that, it's an St.Aloysian fraternity. I remind you, this is the third one in the international series. This is our third attempt. Maybe for the first time in St. Aloysius College as an international seminar in the series. Like, as I said, it's a third one. I'm so happy because as Sinha sir was just mentioning that he can see many friendly faces in this crowd. I always wonder, I don't know how this or whether it's possible for the mathematical fraternity to be very friendly, more than that very hostile. Because myself, always I said that it's not easy to deal with this mathematical fraternity, but not like Jason and all, it's very easy. That's why I always wonder, how can you be very friendly? But I feel that it's very friendly because that's why you are coming over here. I'm so proud and so happy to come to this occasion, to be this inaugural session, to inviting you all, and at the same time wishing you all the very best. This is an, what do we call? You can be in your own safe zones or comfort zone without any updations, without any radical changes. What you have learned in your classroom, like a gymnastics, any other things, you can be satisfied on. You can be in the margin or in the periphery of this topics or academia, what you have taught and learned. But more than that, when you come for a workshop, come for an international or national conferences, that means the collaborations that make you more, your horizon will be widened. There only you can do anything. That's the thing, make any subjects interesting. I use the term interesting. I don't know whether, have you ever heard of, what do we call, chirping of this a seed. Once you plow the seed inside the mud, you might not be much listening to the process of growing. Being an zoologist or being a life science department one, I always pay attention to this one. It's very beautiful. The same way, I have been witnessing this mathematics department and their activities, especially in terms of this international conference and the very inception, the first day itself. They are working in a tremendous way. So really hats off to this mathematics department, especially Dr. Jason and Dr. Narayanan and all other teachers. And this year, it's like a cherry in the cake. We have been recognized and awarded as Research Center under the Calicut University. This is an auspicious occasions to recognize that too. So once again, I wishing you all the very best, especially those who have come across, especially overseas travelers. Let it be a beautiful moment. And I remind you that collaboration is the language of the day. Especially in academic corridors, collaboration is the language. Make it more convenient, make it more fruitful in collaborating each other, in discussions, in topics, in dialogue. Especially, I always cherish you, I'll always welcome you to the campus also. I don't know whether it's possible, but make it or ensure that before you leave, just come to the campus. It's a beautiful one. All your mathematical, gymnastic and pressure and tensions will be released out of that ecosystem, especially in the environmental, it's in the lap of the environmental beauty and serene. Now college is standing. So always welcome to the campus too. Wishing you once again all the very best. Thank you.
Thank you, Father.
Lastly, I invite Professor Chapo Joseph, our former principal, for felicitations.
Good morning, Professor K.B. Sinha, Professor Krishna Madley, Reverend Father Thomas Chakramakal, Manager of the College, other dignitaries on the dais, and distinguished delegates. 4 years back, when Captain Dr. Jason and his team of mathematics department approached me and said that they would like to organize an international conference. So when they initially put forward the idea, I was not so optimistic about the idea because this is a place where higher level research and academics is taking a back seat, and many other silly issues gain front seat. That's the academic circle that we have in Kerala in general. But when they showed me the proposal and how they would like to collaborate with the leaders in mathematics, I thought, okay, let them go ahead. And finally, when the event happened, I should say that I was really surprised to see so many distinguished delegates and speakers coming to the event. Then last year, before the conference, when it was announced, a friend of mine who is a senior mathematics faculty called me and asked, is there a big event being organized by the Department of Mathematics with so many eminent speakers coming? So I was really proud to hear that, because he said he had calls from friends even from outside India asking about this conference, and now we have the third one. I can very well tell you that not even the universities in the state of Kerala has ever been able to organize events like this, that too 3 consecutive events. So I would like to congratulate Dr. Jason and his team for organizing this event. And as already been mentioned, this department has now become a research department. So mathematics research, as I understand, is having many constraints because of lack of good candidates. So I think these 3 conferences that has been organized by the department will be the cornerstone in their way forward, because I'm sure they will be organizing another one next year, and the researchers who join will join the students and the team of teachers to organize the next event. So I wish all the very best to the department, and being a faculty of economics, mathematics has always been close to my heart. So in that way also, I'm happy that this event is happening here. So I once again congratulate the organizers, and I hope the deliberations here will contribute in generating new knowledge, because Kerala is now claiming to be a knowledge economy. So I hope it will generate will contribute to generation of new knowledge. Thank you.
Thank you, sir. To conclude, I request Dr. Jasmine Matthew, Assistant Professor of Department of Mathematics, to propose the vote of thanks.
Respected dignitaries, esteemed guests, dear colleagues and participants. On behalf of the organizing committee, it is my honor and privilege to propose the vote of thanks for this wonderful inaugural function of ICOST 2025. First and foremost, I thank the Almighty for blessing us with a wonderful morning and gathering for this prestigious event. Our sincere gratitude to Captain Dr. Jason Jacob, the captain of the department, for initializing this significant conference and guiding us with his vision. We are deeply thankful to our principal, Dr. E.D. Dias, for his valuable presidential address and set a strong tone for the conference. A special thanks to Professor K.B. Sinha, our esteemed IAPC member, for his inspiring inaugural address. We are also immensely grateful to all those who honored us with their felicitations: Reverend Father Thomas Takramakal, CMI, Professor Krishna Medali, Reverend Father Arun Jose K, CMI, and Professor Chaco Jose P, for their encouraging and motivating words. We, the Aloysius fraternity, is thankful to Anusandhan National Research Foundation, ANRF, formerly SELF, for providing the funding for travel and other expenses of the conference. Consecutively, for all the 3 conferences, we are happy to say it proudly, for organizing the conferences. Also, we thank KSCST, Kerala State Council for Technical Education to provide the funding for executing the conference. Now, our heartfelt thanks to Dr. Narayanan PA, the convener, for his hard works and commitment in organizing this event. Thanks to all the faculty, volunteers and staff whose efforts ensured the smooth conduct of the program, especially our students, PG students. We thank the management and team of Lali's Residency for providing all the facilities for the smooth conduct of the program. Last but not least, I thank you to all the participants and guests for your presence and enthusiasm, which truly makes this conference meaningful. We look forward to a successful and fruitful conference ahead. Thank you once again and have 3 wonderful days with a vibrant academic community. Thank you.
Thank you, ma'am. Thank you everyone for your presence and participation. We wish ICOST We wish ICOST 2025 a successful and enriching experience for all. Now, inaugural ceremony will pause for a tea break. Refreshments are available outside. We will resume with the next session at 10:30. Please return to this hall at 10:30 sharp. Thank you.
He is going to talk about resolutions under rank 1 category. He may modify the top title as he goes along.
Well, I will explain you all. I guess you have not been able to speak, but I guess you can hear and there to reach. So, let me first explain the title. Actually, there is no confusion. The first part is the same always. This work is a very good subject and the experts who is studying I started working with one of my ex-students several months back. And then when the work was coming to completion, I left India, I was abroad for the next 1.5. When this meeting for this conference came, the final part of it, and I had to give a title. And I had forgotten what the title that I asked him to put on the slide. So I asked him this title, this slide modification of it. But historically speaking, I would that would have been a more appropriate title in my view. Because the subject, what is there is a resonance going on between this and that.
So you have to hold the microphone a little closer to your mouth.
Okay. That's better. So, this is a very old subject, and I get the indulgence of the experts in this particular area here, and there are a few of them, because they will recall that this subject goes back to almost the beginning of quantum mechanics. Which, by the way, is celebrating its 100th year this year, or maybe last year, I'm not sure, no, this year. I think Schrödinger wrote his famous paper in 1925. So, of course, as everyone knows, the subject is not created at the instant of time or given in monitor. That paper is considered for official revision at the beginning of one. So this is the 100 years. Can you hear? Even closer. Okay. So it is the centenary year of quantum mechanics. And I think the relevance was started being talked about probably as early as 1930s, and then it gave me a better theoretical explanation in maybe 1950s. So it is a very old story. Physicists had their own way of understanding the problem. This is like very close to yes, but you want me to do what it is? Switch it off or keep it here. How do they store it? Okay. So, physicists understood it in one way. I will briefly describe some of those attempts. And then more mathematically oriented people later on, several decades later, started trying to understand it a little more mathematically in the terms of spectral theory, what has come to be called spectral theory of Schrodinger operators. And various attempts were made. I will mention one notable attempt by Howland in the sense of what has come to be called spectral concentration. Now, that can be precisely mathematically defined. What do we mean by spectral concentration? So here we are considering a class of unbounded self-adjoint operators in a Hilbert space. Often it is a explicit Hilbert space like anything over some say real line or Euclidean space and so on. And there this self-adjoint operator is expressed explicitly. And then you have the spectrum. The question is to study the details of the spectrum, particularly the continuous part of the spectrum, in contrast to what physicists in the initial days were primarily concerned with, namely the discrete spectrum of the eigenvalues. So the study of continuous spectrum involves a detailed study of what is known as spectral density. And spectral density function depends on the vector and of course the who is the culprit now? Me or that? I mean, it is impossible to keep the mic at exactly a fixed distance from my mouth. It does vary a little up and down. I hope that I'm not so sensitive to that. Okay. Now, so this will provide a very elementary model which has been studied again and again, beginning from 1930s. By Friedrich, that is called Friedrich's model in honor of Friedrich. You studied it first, so let me start. So this is essentially the organization of my talk. The background, aim of the talk, and or the history of the subject. And then calculation of multiplication operators in the the spectral density of the model and the asymptotic property. Then calculation of the Laplacian operator is equal to R3. For simplicity, we have taken R3. And then label of what is called scattering cross section by physicists and what is called time delay in the scattering process. You see, these are all physical objects in the sense of flowing in a particle at another. Classically, also this happens. You have, say, the center of scattering, and you throw a particle or a ball at it, it bounces off and goes in one direction. Your object is to predict how much of that goes in a certain given direction. Given the model, you have to predict how much of that initial projectile goes in this direction and how much of it goes in another direction. Secondly, there is a delay between but had there not been an obstacle, it would have gone straight through and would have taken certain time to go from point X to point Y. Now that you introduce an obstacle, you will go from a point X to point Y with a different time. And that difference is essentially called the time delay. As if the object is suffering a delay in propagation. So these are very physically backed quantities. Okay. So this is the history of some of which I have already said, except that Schrödinger in his first, in his 26, which is 25, he did calculated the speed spectrum without alpha equal to 0. That is what is called hydrogen atom. Again, by revolutionized physics. He obtained the eigenvalues of the what is called Coulomb Hamiltonian with alpha equal to 0. Now this is L2 over 3 in physical space. So x1 is the direction 1. So the coordinate tells me x1 is 2x. So this is when you have a hydrogen atom and you apply the electric field in direction x direction. So you have changed the object. So your spectrum will change. So this is the self-adjoint operator. And he also studied that. But his study was solving the partial differential equation and studying its properties in various ways. Not in the sense of operator theory as you understand it today. And he obtained the eigenvalues of this. Now we know this operator has no eigenvalue actually, it is all continuous spectrum. So what did he mean by when he said he got eigenvalues? So that is very important to understand what he was thinking. So to understand the phenomena, we studied the decay rate of the ground state. Ground state means alpha is 0. That has a certain number of discrete spectrum eigenvalues. The ground state is the lowest eigenvalue. That vector eigenvalue related eigenvector is called the ground state. So these are ground state. How does this perturbed Hamiltonian with alpha not equal to 0, for which it is not an eigenvalue, how does it behave as time changes? That is the question to ask. And so he did give some idea about looking at such a decay. But as I said, of course, when you know the physicists, we are not interested in doing theorems, we are interested in getting approximate results which you can compare with experiments. And Westbrook came to physicists. Then to find what, remember what Schrödinger said. He thought he was getting eigenvalues. When we know there is no eigenvalue, it's continuous. What is the problem? Why is that? How to correlate them? Remember Westbrook managed to understand from physicist point of view. They looked at what we call the scattering amplitude and established its connection with the pole of an analytically continuum S matrix. But these are words which we do not have an mathematical definition at present right here, but can be defined mathematically precisely. And that they show approximately. Now emphasis word approximately. What do you mean by approximately? When you are a mathematician, you have to make sense of that word approximately. Even by the Cauchy type of Cauchy distribution, it will show. And this is called, in the physicist terminology, called Dirac-Wigner model. Now, the corresponding time delay, which I had mentioned earlier, show a similar behavior with the resonance of R. Now, lambda R is precisely what Schrödinger had thought were the eigenvalues, but there are no eigenvalues. this is the model we are looking at. Now we are talking essentially in mathematical language. So the nx is the multiplication operator by the independent variable x. So this is a very simple operator. It is unbounded, self-adjoint, and has all real line aspect. And then alpha is the scalar, and then we have this rank 1 operator given by the vector q, which belongs to the operator. And there we impose properties on q such that it has an eigenvalue for a certain number alpha naught, alpha equal to alpha naught. And then we let alpha change from alpha naught. What happens? Now, so this is a joint work with a student A myself, my ex-student Elthuruth and A. So before going to this model, we discussed a mathematically precise result by Howland similar to case time. And I had also pitched in with one of my last work I think in this area with water rain and who has been my collaborator for a long time. I have been trying to look at, I think, world it was taken in the 90s, so 30 years back. Sometime they and the next slide, please. Howland is work. We considered this abstract setup. H alpha equal to H0 plus alpha in the scalar, alpha times E, and E is a finite time operator. And this result is the following. If you look at the P naught in the eigen projection for the eigenvalue of H alpha and alpha naught, which is at lambda naught. For alpha equal to alpha naught, there is an eigenvalue at lambda naught. And if R alpha and D alpha denote the resultant and spectral measure, I trust this is will known to most of the participants, what is the resultant and what is the spectral measure associated with this effect. Next slide, please. This is how that's true. If we give an open interval around the eigenvalue, lambda naught, then what is Uj are those vectors which are generating the perturbation? The P is the projection of the complement of the eigenspace. So this is bounded. Here is an open interval. And this is the spectral density. This way is times 5. 5 is the eigenvector. And this vector density is essentially mounted away from the coordinate. And then there is an existence statement. There exists a function lambda and alpha defined on an interval around 0 with lambda 0 equal to lambda 0 to 1. Now we are around lambda 0. So that lambda and 0 is lambda 0 and alpha is absolutely positive for alpha not equal to 1. Such that here there is a number of intervals with the limit measure of the alpha going to 0 and this vector density has this asymptotic form. So this is an asymptotic expression in alpha. Absolutely. Okay, I would say this is one of the highest precise results in the sense of asymptotic expansion. So this is a definition of vector concentration, and there is a little more general definition of vector concentration. But this will do for us. H alpha is a family of vector operators, and lambda 0 is the eigenvalue of H naught, that is alpha equal to alpha naught. We say that the spectrum of H alpha is concentrated to order P. Lambda naught, as alpha goes to alpha, goes to 0. If there exists an opening family of unperturbed operator E alpha, that is why the index alpha, for the interval A alpha. Notice there is alpha dependence in the spectral family as well as the interval. So that makes it a little more complicated than the equation. That converges to the spectral projection, to the eigen projection at lambda 1 as alpha becomes small. So this convergence is strong convergence of family of projection. So this is a little more precise definition of concentration. In general, there is no P that just convergence statement, not order P. Order and so on. Okay, this is a sort of a quick background to scattering theory, what is called. Multiplication operator or a test class operator. Okay. Thank you. So these objects are going operators. Okay. They are defined as strong limit of these unitary groups. E raised to the power ITH. So these are the unitary groups generated by a self-adjoint operator by a functional calculus. So e to the ITH and then e to the minus ITH H naught. So H is the perturbed one, H naught is the unperturbed one exists. So if these limits exist, they are isometries and they are called complete if their ranges are equal and equal to the absolutely continuous subspace with respect to the operator H. So this again needs a little bit of background of knowledge of the splitting of the Hilbert space in terms of the various kinds of spectra. Now there is a lot of confusion sometimes which must be avoided. This is not a partition, disjoint partition of the spectrum. It is the orthogonal direct sum decomposition of the Hilbert space rather than the spectrum. So you can have a eigenvalue inside the continuous spectrum. That does not preclude it. The scattering operator is defined, or sometimes physicists call it S matrix. In fact, if I may be allowed this diversion, I do remember reading somewhere. I think 1920 still in Germany, Munich, where there was a very famous laboratory or school run by a very famous physicist, John Feld. And Heisenberg was an assistant there, just finished PhD and was beginning his research career and got interested in these objects which came from experimental observation, and he arranged them in the form of array of numbers. But he didn't know what to do with it. They looked interesting. But his senior colleague, Max Born, both of whom later on became very famous physicists, winning Nobel Prizes each. Max Born took a little leave and went to Göttingen, another famous university in Germany, where Hilbert was still around. And Hilbert was lecturing. He went to those lectures and wrote a letter to Heisenberg. You know, these mathematicians, they have an object called matrix. And they know how to multiply them.
Maybe you can try. The jargon of physicists. A mathematician had discovered matrices several decades before, in another context. So physicists took that terminology and kept on using the word matrix, like S matrix, density matrix, and so on. It has a history of, I find it very significant history. And so the scattering operator is a more modern terminology, mathematical terminology. Physicists call it S matrix. So this is defined this way. This is unitary only if the completeness is already proven or assumed that a range of omega plus has to be equal to range of omega minus. Then it is a unitary and commutes with the unperturbed object, namely the Laplacian in this case. And when you have this, because of spherical symmetry of the Laplacian, the invariant under the rotation group, therefore you can split the unbounded self-return operator as a kind of a continuous superposition of operators. So it is a bundle of Hermitian operators. So that is the section of the Hamiltonian for each lambda. Okay? So this is, had this been an eigenvalue, then you will have a direct sum decomposition, and that is called diagonalization in more conventional matrix theory. This is a more generalization of the concept of diagonalization when you have continuous vector. This was introduced by Feynman. He called it direct integral. So S sub lambda is this fiber. But it is not a scalar, it is an operator in the degeneracy space L2 over the unit field because of spherical symmetry. be successful. So this is a kind of alternative approach. So motivation is something like this. So if let us consider two variables which is close together, then we will be localized perspective. So with corresponding line function is something like this. So because this is exponentially localized, so what is with very small limit. In case of the localization and if two eigenvalues are very close, then we can somehow do the corresponding localization center apart. This is the kind of one over square root of so that we can expect two eigenvalues are equal. Actually, if I give this code in another, what of the probability to ask that why eigenfunction localization are. So, technically speaking, this is coming from the use of linear mean. So, I ask myself, under this question, why linear mean? So, it is just from the computation, but we still are not able to explain what linear mean is in the physical sense. So, actually, I have no answer. This is still a big devotional answer. Anyway, if this idea extended then we can expect these eigenfunctions are overlapped. Then the eigenvalues should correlated. Which means that if we start also, if we consider the correlation of near eigenvalues, it should give us some information of the localization or some difference. It's actually theoretical physicists are working under this idea. So that we can study the eigenvalue spacing distribution. So the spacing distribution is spacing distribution like this, then it is very anticipated for home. And if the spacing distribution is like this, this is the distribution of then, okay, this is something like so that is the actually, since it's really working under this, we don't know if it's true or not. But it happens in real physics. Okay, so next I'd like to quote a very basic concept on the technical side. So, first we break down to the finite constant and boundary condition and consider the eigenvalues. So, because this is a finitely dimensionalized matrix, we have eigenvalues. So, this is a random variable because H is a random variable. So, let us keep out the eigenvalues uniformly at random. Then this is the corresponding distribution. So let us consider the infinite volume limit. Actually, it's converted to some deterministic with the density as the physical cycle of the field. This is what we call the residual expression curve. And with energy, this is the cumulative distribution function of the constellation. This is called the integrated So in the localized region, everybody is available. It is very natural to expect the personally everybody is available. So this is the known part before. In the case of localization, the localized So this corresponds, mathematically corresponds to the study of the local through atomic physics. So globally, some atoms in the very so this is the physics of our before I show you the results, I would like to introduce some typical learning process which appears in the story. First one is the work process. This is the atom physics. Sitting in the integral point plus shift t. T is the random particle. So simulator is the most interesting. So let us introduce the Gaussian data, which is the random point. So that's the theory of random point is the Gaussian multiplied by the value of the determinant. One point zero to 2009, they think that after one scaling, there is a scaling for the time data. This means this limit depends on data. This is a positive number. I mean, if the data is very big, then very strong result on so data
much. So hope we use that resource regards to the distribution of the data and sample. So data, you can expect as data goes to TV, attached to culture, so we can expect time data going close to growth process. On the other hand, when data goes to zero, then such data is unavailable. So we expect the time data can be performed. Actually, it is the case. It is possible mathematically to prove that time data converts to growth process with uniform growth process as data goes to TV. And on the other hand, as data is zero, time data converts to Poisson. This will become a uniform distribution. So, time data actually interpret. This is the line between the most deterministic state and the most random state. So, the kind of the interpolation. So, what happens in this Hamiltonian? Actually, so this is easier to understand. It is easier to understand to just look at the table. So alpha is bigger than 1/2. This is potentially weak. Then specialized AC, then statistics is strong. If alpha is less than 1/2, it is potentially strong. Then specialized point and statistics is strong. And in the critical case, we have the weak, sometimes the singular continuous, sometimes the point. And it goes for time data. So it is very constant. Technically speaking, to do the growth process is more so easy. And to do the Poisson conversion more difficult. This result is most interesting because it corresponds to the extended space. So this is, the proof of this is not appreciated, but this is because very natural consequence. Technically speaking, this is most difficult. This sometimes happens in the Okay, so I just would like to have a comment on this result. So the critical case we go to time data, and this data is a function of the reference energy. And it changes when we change the reference energy. So this is the picture. Actually, data as a function of reference energy. This is a historically monotone and smooth function, and goes to zero as data goes to zero, and infinity as e goes to infinity. So actually, the critical case corresponding eigenvalue statistics to goes to correspond as zero energy, and it goes to process as energy goes to infinity. And pure point case corresponds to data is less than 2. Singular continuous corresponds to data is bigger than 2. So that the critical case, it corresponds to the GUE statistics. So this is a kind of interesting, you see, that the critical case corresponds to GUE. Then I would like to emphasize that in this case, transition of our point process is continuous with respect to the parameter. So actually there's a interesting connection to the random matrix theory. So in this community, people are studying the behavior of the data sample at high temperature. Usually in the random matrix theory, L is the system side and data is the inverse temperature. Usually data is fixed, but recently people are studying the case that the product of L data is constant, which means that as L goes to infinity, data goes to 0 at the same speed. So it corresponds to the high temperature limit of the data sample. And in this case, there are many studies. Actually, I'm actually involved with them. There are many studies on many data samples, such that the local value statistics is performed. And there's a, they can, it becomes a function of C here. And C, actually, this is also the interpretation between the Gaussian and semicircle law. So Gaussian distribution is a very standard thing. The semicircle law is a counterpart in the free probability theory. So as C value changes from 0 to infinity, so this density of state goes to Gaussian and semicircle. So actually, this theory is a kind of interpreting between these two main probability theories. So there are many interesting research going on under this point of view. Oh, and this is another recent topic by the people around Professor Spohn, so that GGE is a generalized Gibbs ensemble of the discrete total flow. So the stationary distribution of GGE, this can be computed explicitly by this density. So it has a unexpected, very interesting connection between these two theories. And actually, you know that total flow has a very strong connection between the discrete shading of the theory. So actually, I'm hoping there are lots of interesting topics still remaining in this subject. Oh, don't have enough time. So now I finished to recall our previous results. So let us go on to our today's topic. I would like to discuss 3 topics: three-dimensional decaying model and random polymer model. So this is Peter Hizro will talk in this afternoon. So I will skip this. And this is something another one. So I would like to start from the three-dimensional decaying model. So potential decays at x to the minus alpha at infinity, and this is our usual. The usual definition. U is a common distribution. So let us mention on the density of state. So let's use dx is the density of state data of our decaying Hamiltonian. And mu0 is the corresponding one for the free Laplacian. So let us recall the fact. If alpha is 0, alpha 0 means alpha 0, so this is 1. So alpha 0 corresponds to the usual IIT model, just the usual Anderson Hamiltonian. So usual Hamiltonian, as I recall to you, the support of the density of state measure is equal to our almost sure spectra. This is written explicitly. However, if alpha is positive, I mean decaying case, then Dorai, he is, but he proved that density of state is equal to the free Laplacian density of state. It's very interesting that. So it means generically, these two guys are different. So the situation is very different. So the usual Anderson model, the spectra is like this, and this is equal to the spectra support of the density of state. Nevertheless, for the decaying case, spectra, so this is the spectra of the finite free Laplacian spectra, and support of the density of state is equal to this. So we may have another spectra which is outside of the support of the density of state. So actually we may have we do have the Anderson localization here, which is different from the support of the density of state measure. So it means that it is in some sense not easy to detect, to study this region. So maybe I can okay. So this is a typical picture. So if potential is 0, then we have a lot of degeneracy on the free Laplacian eigenvalue, such that points are sitting here, and the typical spacing is 1 over system size, 1 over L, sorry. And the order of the degeneracy of the eigenvalues is typically L to the t minus 1. So if I put some if we put the decaying potential and the weak conservation, then each degeneracy is split. And the order of splitting, we expect this order. To study this situation, we would like to consider 2-point process. The first one is scale by L. It means that to squeeze each cluster into one point, because I scaled by this. It corresponds to consider this point process. So this is the scale eigenvalue. But because the degeneracy has this order, so I divide by this order. The second one is scaled by the literacy. It means that we zoom in, we pick up one cluster and zoom in into this. So this one. And for the one dimension, these two lines are equal and goes to clock process. However, for the d-dimensional case, this is the partial result which I have so far. For the dimension is 3 or bigger, alpha is big enough, then this beta goes to some constant, artificial constant times clock process. This is the best thing I can do so far. And for the to see, I have no results so far. So it turns out to study this one is very difficult. So I would like to postpone study. So to do something different. So next I would like to study the extreme value statistics. So I would like to explain to you the motivation to study the spectra outside of the free Laplacian spectra. Then, as I told you, this is the same as Professor Minami did. We took some reference energy and consider the limit of Tsukushi. But because density of state is zero in this vision, of course, Minami's technique works to some extent. But the result is that this Tsukushi goes to zero. It's a kind of point process, but it's just a trivia. It's not interesting. So we do something different. I would like to focus on this high ops argument goes to infinity. So the usual case, this is the spectra of the finite box random shading operator. This is typical one, alpha 0. And H0 converts to the strong resolvent sense to the infinite volume Anderson-Hamiltonian. It means that in some sense, this eigenvalue converges to the spectra of the free Laplace, spectra of the infinite volume operator. This is a typical thing. But I would like to consider something different one. This is correspond to high energy eigenvalue. As L goes to infinity, it goes to infinity. So it does not remain in the infinite volume operator. So it is not visible in some sense. It is not in the user. So let us study what happens in this storage eigenvalue. So this is just a notation. I consider some scaling. Because this eigenvalue goes away, so I have to consider some scaling. And this is the distribution of the potential, and we have to consider the heavy field. So mu should be support of mu should be Dept. I mean, it does not decay as infinity, so this is a concern. This is some measure. This is inhomogeneous measure. Density is 1 over x squared, supported in the positive axis. This is the result. This is just a notation before it. So, let us look at the picture. Let us look at the picture which explains this result. So this is our result. So alpha, I can somehow find the critical alpha. And if alpha is smaller than alpha, it means the potential is strong. Then essential spectra. By the way, random potential is assumed to be positive. So we have the spectra only here. We will not have spectra in the negative part. So if potential is strong, then essential spectra is here, and we have an Anderson localization here. And the eigenvalue point process corresponds to this staging eigenvalue. It obeys the Poisson point process. This is the intensity measure, is not a Lebesgue measure. This is the inhomogeneous Poisson process. It's a very strange measure. And secondly, if you analyze weak, I mean, potential is weak, potential is weak. Then, essential spectra is just a free Laplacian spectra, and we only have a discrete, finite number of eigenvalues only. And this is bounded from above. So, very different situation. So this is one result. So we have some further problems. So this is so okay, because I don't have that good. I try to just advertise that there are some mathematical results which prove vigorously the existence of mobility. And we have some corresponding results on this kind of okay. So this is another result. So we have a sharp transition of the localized sharp transition in the eigenvalue statistics. So we have a Poisson process, but at only one point it goes to process. So this is another topic because we don't have the time. I stop here. Thank you so much for your attention. Thank you so much.
So okay, I will talk to you.
Sure. Yeah. You can send me some few for interest topics you're interested in. Then we can.
Yeah. Anyway, we'll let you know.
Sure.
I'll sit in the front. போய் உட்காருங்க என்ன இப்போ எத்தனை பேர் தான் உங்க கூட ஒர்க் பண்ணிட்டு இருக்காங்க 10 15 பேர் இல்லை ஒஃபிஷியலி அபிநந்து சோஃபியா மட்டும் மற்றவங்களாம் எப்படி தான் மேனேஜ் பண்ணுறீங்க இத்தனை பேரும் ஃபுல் டைம் ஒர்க் 2 வீக்ஸ் ஒன் சாஃப்ட்வேர் அட் ப்ரெசென்ட் நோ ஸ்டூடெண்ட் பேப்பரை எழுதி டெலிட்டு ஸ்டூடெண்ட் எடுத்துருக்கீங்க இல்லை இப்போ வேறு இருக்கவே இல்லை சரி மற்றவங்களும் நம்மளோட ஸ்டூடெண்ட்ஸ் கிடையாது சரி சிமியோட ரிப்போர்ட்டில் வந்துருச்சு அது அவங்க சொன்னாங்க சிமி வந்துச்சு நல்ல விஷயம் பேப்பர் சரி இருப்பீங்களா இங்கே தான் இருப்பேன் பார்ப்போம்
Thank you very much. Speak loud. I think speak loud. Speak loud. Thank you very much, organizer, for giving me this opportunity. School of Therapies. First time in this part of the state. I'm a regular visitor of Kerala, but first time here. Apology for this game. I like gold. So I talked about let's get it is the following. So first of all, I talked about P, bounded linear operators. I will say Tj, and I let them commute. Board is so okay. I understand. You have, let's say n is a natural number, and you have n commuting operators acting on some Hilbert space H. H will be separable and over C. And that's my setting. And I say for polynomial, for all polynomial, and for all P, is it visible? All such commuting contraction assume, I'll assume to be contraction, and I'll tell you why. For all B and for all D, on some Hilbert space H, you look at P T1 up to Tn, and you take the operator norm. So this makes sense because Ti's are commuting and your variables are commuting. So you take this. This makes sense. And this is the operator norm. And you expect this to be supremum of modulus of Pz, where Z is coming from polydisk. Let me write this. B means complex number, okay? And polydisk is the product So this is in C of A. There. Okay. So this is my statement. Okay. I'm saying for every polynomial b, for every t, and this inequality works. One important thing, this is I'm just claiming, is that left side is about operators and the right side is about number. Okay. So you can say right side is like a complex analysis object, left side like an operator object. So you want this comparison, and this is a statement. If this works, you call Vn sub n h holds. In other words, I will say one-hour inequality hold for inverse space H for n double. That's a goal or to understand the object. So question is, why you want to do that? First of all, it's a very interesting thing because you have analytic object and operator object. Second, this I will not be able to show. This relates every other aspect of function theory, operator theory, like interpolation problem, dilation theory, and so on so forth. Third is that you can take uniform limit of Pn and you can take on the right side. So this will give you a sense of operators on function. So anyway, no. Contraction is the assumption. Contraction makes sense because you can take P to be Zi, and this will become Ti, and this will become 1. So contraction is essential. That's all. That's true also if you want this Ti force to be contraction. Alright, theorem 1951 Vn1H makes sense. So this is by von Neumann. So von Neumann himself proved that this inequality works in one variable for one contraction. That means norm of Pt less than equals to this. Okay? Okay, fine. Then he used some sort of Carat-Theory's approximation principle, and he essentially proved it for this algebra, not for this. But these are equivalent. If you can do this, you can go to this algebra and vice versa. Now, then let's move to 1953, and let's look at n equals to 1. So my contraction is only 1 on a universe space H, and then I just write the name of Nash. It was a very exciting period of time, and he said if you take a contraction, then you take I minus T star T, which is a positive operator, and you take the square root and you call it T. That will be also a positive operator. And then he inflated the space in a huge way.
infinite sum as follows. This age, this is acting on age, and I say this is a lonely guy, only one, and then he took age, direct sum, and it goes on. I'm saying it's actually he, it was not him, but Sheffer, which came a little later. But idea was there. But you can see this is age, direct sum, M2 of age direct space, or Fox space, you want to say. Yes. Left hand side, thank you. Inflated age. And out of that, okay, so since it is a very small scope to return or no scope to return, please keep this in mind. And then he defined V sub t on H tilde as V sub t. So I will do it in this way. So this will be H, direct sum, that infinite copies of H, okay? I'll do this 2 by 2 dot matrix. Here I will give T. Here I will write T operator and keep 0 everywhere. So this is a column vector. You see that? Because this will be H2, the infinite copies of H. And here I will write 0, all the way 0, row 0, and here I write the shift operator. Shift operator means what? I have defined this. So shift will be on this infinite space. It is the standard one. You take a, so this definition of space is clear, right? You take a sequence which is solved. And the action of this will be, you take the sequence and push it to the right, plugging 0 on the first place. Okay? So this is a standard shift operator. If you look at the matrix, this is what you have seen as a Jordan law. And this is an isometry because it just moves the thing one step, no information gets lost. Alright. So, now a very simple computation proves that Vt star Vt is identity. It's not hard because kernel of Sh star, Sh is an isometry, kernel of Sh star will be exactly this. And this guy is sitting in proper place, and when you hit with Vt star, you will see that identity comes out. And you have to use that P square is I minus P star T. It's very easy, but I don't have a space to compute, otherwise I would have done by myself. Alright. Yes. No. It's a contraction. It's a contraction. But identity star T equals to identity means isometric, that is also allowed. Okay, so what's the big deal? The big deal is the following. With this view, I can write Vt star as T star, right? Something, 0, something. And in general, Vt star power m will be T star power m, something. Saying this, all I am saying is the following, that Vt star power m restricted h is T star power m. And this is true for every integer. Saying this, I am saying the following, that T power m is Vt power m restricted h projected back on h for every n. If you have understood this part, then we can congratulate each other because we have proved a very deep result called dilation theory by Nash. So, this is a theorem by Nash, 1953. you have a contraction, then you can have a dilation. This is a definition of dilation. Now, is there any other thing? Red one, where is the red one? Oh. Now you see, this is theory, okay? But right here, I can remember I started with commuting couple, T1, T2, Tn, they computes, and then what I can do, I can say this is T1 power n1 up to Tn power n. So you take multi-index and take all the power. Correct. And then I can, instead of one single isometry, I can play the same game, which is the multi-index. I just call k to be m1 up to mn. So suppose I have a commuting contraction and I have a commuting pair of isometry, and if I can play the same game, I will call isometric dilation modes. So I will write I, E, N, H modes. Is it clear? This should be D1, D2, Dn, commuting pair of commuting tuple of isometries. If you can get, then we say this. So, what I can say, Nash proved that isometric dilation 1 on H works. This is what we proved. And then we raise the following question: can you do it for 2? Can you do it for 3? And so on. Those are questions, like for now. Okay? Now, what I want to prove is the following. I want to prove this ID1 implies 1 1 8. I want to prove. And that was one of the motivation of Nash, that he wanted to be an operator theoretic proof of this problem. Okay? So, proof that ID1H implies 1 and 1H. So I have again norm T less than equals to 1 in H, and then I start from where I end here. I start with the isometric dilation, and I figured this is true. What I figured is that T power m is T power n restricted H projected gamma H. This is true for MPL. And then I go a little bit at place, very small trick, thanking to Helmholtz, who did this before everything came up, okay? So Helmholtz, if you recall Helmholtz, I define U to be B I minus BD star 0 minus D star. And I can prove this is a unitary operator. And what I can say further, that this, I can simply replace B by U. It does the same job. In other words, I can replace the isometry by unitary, by thanking Helmholtz. And before passing, I remarked, thanking to Ito, I can play the same game, once you come up with a isometric tuple, I can replace it by commuting unitary tuple, by Ito. So in other words, without loss of generality, I can assume V to be unitary, which does the same job. And I erase this. This is Helmholtz, and in several variable, Ito. Okay, now this tells me something interesting. This tells me if I take a polynomial one variable, that will be pH, polynomial V, restricted H. But I'm interested in computing the norm of PT, that's what my inequality is about. So I take the norm of PT, right? That is the norm of this. Now you evaporate this by inequality and you get this is less than equals to norm of PU, right? But PU is a normal operator because U is a unitary. I have replaced my V by U. Spectral theorem picks it. And spectral theorem tells you this is the soup of what? Of lambda belongs to spectrum of PU, right? Modulus of mod lambda of this. Oh, no. Mod lambda is the spectrum of the normal operator. But then, spectral theorem picks in and tells you that this is as same as saying soup of mod of P lambda, where lambda is in the spectrum of U. Right? The spectrum of U lives inside the circle. So you can finally say this is lesser equals to soup of mod of P lambda, where lambda is coming from T. But that's it, because then you use maximum modulus principle and you say this I can replace it by the disk, and that's the formula. So what you do is that isometric dilation forces fundamental inequality, right? In fact, it proves little more. It proves complete fundamental inequality. You can prove it for matrices also. That is something called complete spectral set, which I am not doing. So now the question is, so okay, now we have settled down. We have figured that isometric dilation, one works for them and one works for every inverse space. What about more than two? Right? Now I have at least showed you one or two groups so I can proceed without afterwards. So here is a theorem. I suggest you look at the book by PCA, similarity problem. There you will have a very elementary proof which I think you can give it to college students. I don't have time, otherwise that I would have given. That proof goes to Nelson, 1961, in one of the proceedings in this paper. Beautiful work. Okay. I suggest because soon I will give you to the world of question and you never know which one is going to help you. That IT2H works, and I told you the method I showed you. If you have isometric dilation, you can always get fundamental inequality. Some copy-paste proof, nothing new idea, no new idea needed. So this also works. Fundamental also works. And this is a very celebrated work by Anglo, 1963. But the trouble is that this is a mysterious result, because even you take a commuting pair of isometry and you use Anglo's theorem, what you get is not very clear. That means the structure of commuting pair of isometry is a very mysterious object. In fact, if you understand commuting pair of isometry, you can solve invariance of space problem. So, it's that subtle one. Okay? Now the question is, what happens in larger than 2 or larger than equals to 2? Here the things started getting very different and very muddy. Okay, so 1974, Kaiser, ALS, and Vadopoulos. They said that mononomial inequality at the level of 3, that means 3 there. At the level of C5, that means on 5-dimensional Hilbert space, tells. And here things started getting very different. So you understand this? That means there exists a 3-tuple commuting constructions on C5, that means 5 by 5 matrices for which polynomial inequality fails. Let me write this matrix because this matrix is a bit of magical. Okay, so let's call alpha as 1 over square root of 3. My Q1 is 0, 1, 0, 0, alpha 0 and beta 0. So this is the 3 by 3 5 by 5 matrices, and with this matrix you take the polynomial as zi square I of 1 to 3 minus 2 zi zj I less than j. It's a 2-degree homogeneous polynomial. At that very simple level, at very simple 5 by 5 2 matrices, you with a very little computation, you can do formality tests. Right? And this example is interesting because many people played around and created many other different examples. Now, this is polynomial inequality tests means, in this case, isometric dilation doesn't exist because that will force polynomial. So you can also replace by IT3 on C5 also fails, right? Now the question you can turn around, maybe there is a chance that it is always the case. That means polynomial will fail only when the isometric. I will write in here. IDN will for n tuple, yes, for n. That will imply VN. Yes, so this will imply this. No, if I write 3 here, no. I use the isometric dilation proof, which I did for one case. If I can have isometric dilation for let's say 5 tuple, then I have fundamental inequality for 5, right? Not more than that. I use that. Okay? Yeah, this n and that n are same. Okay, now there is a very amazing example by Carol, 23 years. Maybe I write here. Sorry. Carol is a little before 1970, and he again came up with a very interesting example, almost very trivial. It is like that you take a Hilbert space whose dimension is larger than equals to 2. So you can stick to two dimensions, no problem. And you construct H tilde as H direct sum H. That means you can be on C4 and onwards. That means C4 and onwards allowed. Okay. Then you do what? You take X on H, a contraction. And you take U on H, a unitary. Such that U is not in the commutator. You can always do that. You see also, you can find immediately and a construction, they don't know do that. Okay? And then you write this matrix, impotent 0, 0, I, 0, T2, 0, 0, X, 0, and T3, 0, 0, U, 0. With this example, you can prove that I, T, 3 over this H tilde tells. But formula inequality works. Formula 3 over H tilde works. I'm sorry, this is bad, perhaps bad notation, but there is no space. I write all the statement here. Okay? But you understand what I'm saying? For this couple, this three couple, you can prove that there is no isometric exception, that dilation, but you can still have the fundamental inequality. So you made the matter more complicated. And what is very interesting, in this case also, he used some sort of homogeneous polynomial. A lot is going on with homogeneous polynomial. A lot of E hidden in the homogeneous polynomial. Okay, now the question, question is that C5 failure, so C4 I said, fundamental works, but isometric dilation doesn't work. But then the question is that at the level of 4 itself, is it always true that fundamental works for any couple 4x4 matrices? So you take a couple of 4x4 matrices. Is it always true fundamental works? You cannot ask isometric dilation because it fails. And quite interesting. Although not so long ago, 2001, he proved that fundamental for three tuple at the level of C4 also fails. So there exists, this happens but not always. And in this case also, the same homogeneous polynomial works. And his example is not very far from Kaiser-Paratula's example, that matrices. And he used Elthuruth factorization theorem, where you expect norm of the product of matrices equals to the norm of the product of the norm of the matrices. Means norm of AB equals to norm A times norm B, which of course doesn't work, but for there is a Schur product you are talking about, and there is a Elthuruth tensor product technique you use and get that. Little deep, not trivial. Okay, now the question, how you go C3, C2, those are the cases, right? So here is a even little earlier, Drury in 1970, using technique of Schwarz lemma, he proved that fundamental inequality as n couple at the level of C2 works. That means if you are talking about 2x2 matrices, fundamental inequality for any n couple will work. And after 10 years, I'll look again. He proved that isometric dilation for n over C2 also works, so that this is not an accident. Now the situation was aligning C2. Sorry. So the remaining case appears to be C3, and quite interestingly, that got a very important turn. Now, here is a 20 2030, showing, and there is showing as in a very, very smart mathematician. Counter example, you just talk to. They said that IT IT for 4x4 at the level of C3 pairs. That means there exist 4 3x3 matrices for which construction, computing, all those things, for which you cannot have an isometric dimension. Okay, that's the very quite ingenious counter example because that doesn't quite fit with Kaiser Barbaros time. And then a bit of interesting story. In 2015, Kosinski, he came up with a paper which talks about 3-point interpolation of the polydisk, and that was about it. And he did a lot of mathematics, very deep, and he published the paper got accepted. And then, Greg Lees, in 2016, he said, he pointed out Kosinski that, look, your technique has proved something interesting, which you missed. It is the following, the fundamental inequality for n tuple at the level of 3x3 matrices always works. But perhaps Kosinski was not very aware of perhaps, or he was not looking to solve this problem, but he solved something I told you that interpolation and fundamental are closely related. So, and when Greg pointed out that to him, he said, you just write a remark. Kosinski, as a very nice gentleman, said, forget it, you observe it, you write. So, it is his result, but you can give the credit also to Kosinski, because Niels himself also gives this credit, and it is quite unique. So, now, there is a dilemma. The dilemma is, if you look at this, and if you look at Choi and Davidson, there is one question left, which I tried with one or two people here. We were worked out. So the problem, which is open, is the following. Is it true that this scope is due to isometric dilation? For 4 low, so isometric dilation for 3 on C3 does it work? So I call it 3x3 conjecture or question. This is open. Another open question which now you understand in the realm of this fundamental inequality and isometric dilation, it is a very important question even at the level of finite dimension, that means finite matrices. Just collect a class of finite, n tuple of matrices for which prove fundamental inequality works, or disprove fundamental inequality doesn't work. Prove isometric dilation exists or it doesn't exist. For 3 tuple or more than 3 tuple, even at the level of matrices, is a very, very important problem. Okay? So depending on your class, you will sometimes can hit jackpot. You can perhaps solve some kind of interpolation problem. You can sometimes solve characteristic phasor interpolation problem. There are many others. So this is one take-home kind of question. Okay? What do you everybody is telling their result, but I don't want to tell my result. I can tell you that I have done something small thing here and there. I will not tell my result, but I will tell somebody's one more result which I have done something later on. This is very interesting. So, this is 2005, a paper by Agla and Mappen. And they managed to publish in ACTA. It's very simple. So I just want to give a definition. So what you do, you first pick a two variables polynomial and define V as the variety. This polynomial, there are some care to be taken, like if the irreducible component should not be, should be only occurring only one time, that will be no square or this kind of form for some connected set issue. Okay, let's not get into that. Let this, define this, such, assume V closure, you take the closure inside the T2, okay? V closure, intersection del D2. Del D2, I don't know how to say, okay, this is the topology, this is the distinguished boundary, that means the torus, T cross T, okay? Circle cross circle. This should be equal to V closure, intersection del D square. This is a topological boundary which is massive. That means circle union, D closure union, and D closure union circles. Much topological boundary is much bigger. What you are saying that D closure intersection with distinguished boundary equals to D closure intersection with the topological boundary, topological boundary. In other words, you want to exit the bodies through the variety, you have to exit through the distinguished boundary. That's what it says. So with this condition, you call B a distinguished variety. And the question was, alluding how you classify this kind of object in 1969. And what Agner and McCarthy did, they classified it, and while how you write the, how you write this, maybe I write. Theorem 2005 by Dept that distinguished varieties are given by Z1, Z2 in E2 such that, now I say I will write something, but let me point out that phi Z coming from is given by an n by m matrix whose elements are rational function just for instance take cross states and phi z star phi z is identity on Cn for all z on the boundary. In fact, what we call this as a rational inner function. That's what I'm writing. Okay? So if there exists a rational inner function such that determinant of phi z1 minus z2 I Cn, this is z. So this is the classification of distinguished variety. In other words, what you are saying that a variety, algebraic variety, is a distinguished variety if and only if it is a determinantal set given by a rational inner function, which is quite interesting because how one expect from here you come here. And what they did make this very interestingly. So they picked up given a distinguished variety. they constructed a measure and went to L2 space. And with that L2 space, then they look at the polynomial and take the closure, which kind of become hard space. And then they considered a pair, and that pair becomes kind of an inner pair. And from the inner pair, they use kind of an annotation type of thing to get it. It's a very long way. But for our context, because the title of the talk is polynomial inequality, is the following. For theory, again, by name, let I already said this is less or equals to sup norm of P over P2. I already told you because this is the Ambrose theory. And from P1 we started facing difficulty, right? So what you do, they prove that you don't have to take a sup norm over P2, you can take a sup norm over a distinguished variable in this specific situation. In other words, now you have a different question that given a special class of matrices or operators, can you get or obtain the polynomial inequality instead of looking at all over P2, you just get some smaller set. And most important is that smaller set carries some geometric or algebraic implication. So that is what they are. Okay. So 5 more minutes. 5 more minutes. So then I want to tell you another problem, which is also I know. Let's share 5 minutes. So you get the question, right? So you can play around this type of thing. Even for n double, you can think of fundamental inequality. Not all over quality is smaller. Yeah. Eventually it will be same. See, this represents multiplication by phi, which will be a pure isometry. This represents multiplication by Z2, which also represents pure isometry. So with some unitary equivalence, you can play around and come back to the set. So the real game is that multiplication by phi is actually a pure isometry. And that comes from this strict assumption right here, in this case also. Not touching the topological boundary. Now, for what I have said, I have some little bit contribution here and there, but not in this problem. So this problem is absolutely, I have no idea. So it is the following, and it is absolutely at the matrix level. So A is in MNC, and W of A is the numerical range. It is that inner product AX comma X such that norm X is 1, and of course X is coming from Cn. So this is a numerical range, and engineer people loves it because this is the place where you can find all eigenvalues. And location of eigenvalue is a problem, and this is not a completely out-of-scope set. This is complex and compact, and it is a result in 1918 by Dept and Hausdorff. So one of the very nicest results along numerical range, and I think a lot is going to happen around numerical range in decades to come. And here is a conjecture. This is called a French mathematician, Closets. And this is a question 2004. So he suggests the following. If a matrix, n by a matrix, you look at P of A, where P is a polynomial, and you look at again the same way operator norm. Now there is no contraction, etc. Okay? And he asks, is it true? This is 2 times norm of P, but not over the disk, over the numerical range of norm. This is a question. At the level of finite dimension, very, very nice and wonderful finite dimension. And in that paper in 2004, that I think ICOST, he proved for n equals to 2, this is correct. And also you can prove that you cannot do anything better than these. Because if you look at 0, 2, 0, 0, that matrix will tell you is the best one can think of. But in 2017 or something, he proved that these two, he can go at up to this. So this inequality is 2, so 1 plus square root of 2, but to get to 2, it is not clear how you go. Very secret level message came to me last year that one guy claimed this is to be true and submitted to somewhere, and the referee were secretly checking and passing the information I'm checking, but it turned out to be wrong again. So this is a very open question. Think about a normal matrix, it's easy to do. I think for Jordan law also, it's easy to raise this part. Thank you very much.
I would like to invite Professor Krishnamurthy to the stage to present an oral administration to our stage. With that, the talks from morning session concludes. Now we will have a lunch break, and I request everyone to step outside for the lunch. After lunch, we will resume the talks at 2:20 p.m. So I request everyone to be present in this hall at 2:20 p.m. sharp.